Hi, Algebra 2. Wanted to go back to what we had talked about a little bit earlier this week, thinking about solving polynomial equations, and then today taking a look at a couple of the theorems that help us do that, and then use those same theorems to help us write some polynomial equations when we know the roots. So I want to take back a chapter or so when we learned how to solve quadratics, and one of the first ways we learned to solve them was by factoring. We used something called the zero product property. If we could get one side of the quadratic equation in its factored form, where the product was zero, we knew that at least one of the factors had to be equal to zero. And we could use that to determine what our solutions were to our equation. And it turns out that there are some polynomial equations that we can do the same thing with. If we can go ahead and factor one side, we'll get a series of factors that product has zero, and then use the zero product property. So let's take a look at an example of that. So solve this polynomial equation by factoring. So we have 3x to the fifth plus 18x to the fourth plus 27x to the third equals 0. So we don't have a really nice, neat, easy way to factor x to the fifth like we did with quadratics. However, our first move always is to take a look for a greatest common factor. And I see x to the fifth, x to the fourth, x to the third. So I know I can take out an x to the third from each of these terms. And 3, 18, and 27 have a common factor of 3. So 3x to the third is going to be my GCF. So once I've factored that out, I'm going to have a remaining polynomial factor. 3x to the third times x squared equals 3x to the fifth, so this term is x squared. 3x to the third times 6x gives me 18x to the fourth, so 6x, and then 3x to the third times 9, 27x to the third. So I've got 3x to the third, and then x squared plus 6x plus 9. I recognize this as a perfect square trinomial. So I can factor that, x plus 3x plus 3. So now I have 3x to the third times x plus 3 times x plus 3 equals 0. I can use the zero product property. Each factor set equal to 0 and solve. So 3x to the third equals 0. Divide both sides by 3. X to the third equals 0. I take the cube root of each side, and x equals 0. And here, x plus 3 equals 0. I get x equals 3. So I have roots of 0 and negative 3. Now, one of the things we had talked about was this idea of multiplicity. I have 3x to the fifth. I'm going to find out a little bit later on. I should have 5 roots altogether. Well, 3 of those roots are 0, and 2 of them are negative 3. So there's our 5 roots, even though only 2 of them are distinct. So we can use this concept to be able to solve some polynomial equations. So we learned earlier that we had other methods of being able to solve besides GCF. We used factoring by grouping, right? We used the sum and difference of cubes, which factored as a pattern. And then when we couldn't do any of those, we ended up testing a root. If we could find one factor, sometimes that would knock it down to a small enough degree where we could go ahead and factor this out. So I wanted to take a look at an example of how we did that. So this is a word problem. I don't want you to worry about the word problem so much. I'm really just interested in looking at how we factor this. So I have this equation, x to the third plus 3x squared minus 10x minus 24 equals 0. And factoring by grouping is not going to work for me here. So my next move is I need to be able to determine one linear factor. If I could find one root here, then I could use synthetic division to factor that out and go from there. So we use something called the rational root theorem. 24, or the negative 24, is my p-value, and the leading coefficient 1 is my q-value. P over q, negative 24. So if there is a rational factor, a real number rational factor, it's going to be a factor of negative 24, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, plus or minus 24. That's 16 possibilities. Like, do I want to test all those? No, I really don't. So what I do know, though, is that one of my factors is going to be from amongst this list. So x minus 1 or x plus 1, x minus 2 or x plus 2, x minus 3, x plus 3, and so on like that. So I could do my synthetic division and start testing these until I find one that works. So the book suggests that x minus 3 is going to be a root here. And so when we use synthetic division to find that, we get x minus 3 times this remaining polynomial factor, x squared plus 6x plus 8. We're able to factor that side, x plus 2, x plus 4. So I find out that my roots of this equation are x equals 3, x equals negative 2, or x equals negative 4. So that's kind of the process. If we can't use one of our other methods of factoring, then we test a possible root, we use synthetic division, and we move on from there. So a couple things I want to point out. It's possible for polynomials to have irrational roots, right? Radicals that we can't simplify. And those come in pairs. If I have a plus b times square root of c, I'm also going to have a minus b times square root of c. So they're going to come in pairs. As an example, if I know that 1 plus square root of 2 is a root, then I also know that 1 minus square root of 2 is a root. So moving on, I want to look at something called the fundamental theorem of algebra. And this sounds like super critical. It's like the fundamental theorem of algebra. It's like what everything is based upon. And it's actually not that complicated. So I want to show you this table. It says that these statements are all equivalent. There's a real number r that's a root of this polynomial equation, something, p of x equals 0. Well, if that's true, then when I substitute the value r in, the value of that function is going to be 0. That tells me that r is an x-intercept of the graph of that function, and then x minus r is going to be a factor. If I divide x minus r out of that p of x, I'm going to get a remainder of 0, which tells me that r is a 0 of the function. So all these things are true. And because of that, I can use that to do something that we practiced the other day. If I know the zeros, I can write a simple polynomial that has those zeros. So if I know the zeros are negative 3, 1/2, and 1, I write those as factors. X minus negative 3, that's x plus 3, x minus 1/2, and x minus 1. And then I would multiply those out, and that would give me the simplest polynomial that has those zeros. So that's something that we practiced the other day. Two more theorems I want to take a look at. And this one's not a bad idea to pause the video and write this one down. Fundamental theorem of algebra. So it says every polynomial function of degree at least 1 has at least one 0, where a 0 could be a complex number. Another way to think about that is every polynomial function of a degree at least 1 has that many zeros. So whatever the degree is, there's going to be that many zeros, including the multiplicities. So we saw that example earlier, where an x to the 5th is going to have 5 roots. It just turned out that 3 of them were 0 and 2 of them were 3. And we mentioned the irrational roots. Same thing holds for complex roots. If I have a complex number, imaginary number, as a root, it's going to come in conjugate pairs. If a plus bi is a root, a minus bi is going to be a root as well. So I want to walk through this process. We want to find the roots of this, x to the 4th plus x to the 3rd plus 2x squared plus 4x minus 8 equals 0. So I have no GCF. My constant term doesn't have x as a factor. 2, 4, and 8, that's promising, but there's no coefficients other than 1 here, so I can't factor out a GCF. There's 5 terms here. I can't use factoring by grouping. So my only hope here is to identify possible roots and test them. So my p is negative 8. My q is 1. Negative 8 over 1 equals negative 8. So what are my possible factors? Well, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. That means I could have x minus 1 or x plus 1 as a factor, x minus 2 or x plus 2, x minus 4 or x plus 4, x minus 8 or x plus 8. It doesn't mean that all of these are going to be factors. It just says that if it has a real number root, the factor is going to be one of these. All right. So one way we could do this is just go in and start testing, right? But, it's the 21st century. Let's use technology. So I'm going to go ahead and minimize my inset here. And let's take a look at this graph in Desmos. So here's our equation, x to the fourth plus x to the third plus 2x squared plus 4x minus 8. And the graph suggests that I'm going to have a root at 1 and a root at negative 2. So if 1 is an intercept, that tells me x minus 1 is going to be one of my factors. Okay, so if x minus 1 is a factor, I can go ahead and use synthetic division and go ahead and do this division, find out what the other polynomial is. So remember how this is done. Here's my x minus 1. Here's 1x to the fourth, 1x to the third, 2x squared, 4x minus 8. So remember, I bring down my 1. 1 times 1 is 1. Add going down. 1 and 1 is 2. Multiply. 1 times 2 is 2. Add them up. 2 and 2 makes 4. 1 times 4 is 4. I add these and get 8. 1 times 8 is 8. Add them up. 0. So 0 is my remainder, so I know that x minus 1 is a factor. So x minus 1 times, and then this was x to the fourth, but I divided out 1 degree. So this is 1x to the third plus 2x squared plus 4x plus 8. All right, so what happens now? I look at this, and I could go ahead and test with another root, but I also see that factoring by grouping is going to work for me here. So I have an x minus 1. Here I can factor out x squared times x plus 2. Here I can factor out a 4 times x plus 2. So this factors as x plus 2 times x squared plus 4. And I have an x minus 1. So now, x minus 1 times x plus 2, awesome. And then I have this. Now, I recognize this as something that I can't factor. But I also see that if I took the square root of both sides, this is going to be x plus 2i and x minus 2i. So these would be my 4 factors. X to the fourth tells me I'm going to have 4 roots. Here they are, x minus 1, x plus 2, x plus 2i, x minus 2i. So if I was going to go in and try and solve this, that would be my procedure to do so. All right, so I was hoping to get a chance to get this down on video, so that means that you could pause, scroll back, look at these examples again, stop and write down some definitions. If you have questions, bring them to the next class meeting and we'll go over them.